After looking into some of the key functions of the link layer, we'll now go to protocols. So we know how we create frames out of the bit stream. We know how to check for errors. We know how we can control the flow so that the big powerful computer will not simply swamp the little IoT device with too much data. And we know how we can access the medium, how we can control this, what happens if several devices try to access the medium at the same time. So now let's have a closer look into some protocols. So where do we find our link layer? Well, everywhere. So we'll find it in local area networks, so smaller diameters, some 100 meters, 10 meters, simple connection structure. There we will see, well, Ethernet dominates local area networks. We had historically some other technologies, but in the end we have Ethernet, and we'll see what this means. And for the wireless case, we have wireless LANs, Wi-Fi technology, Bluetooth, plus we have some other network types for industrial control systems. For mid-sized networks, metropolitan area networks covering whole cities, well, there were also historically many different other technologies. In the end, today, what do we see? We have, again, Ethernet, and also in the wireless domain, we have, for example, LTE 5G networks. And for wide area networks, so the networks connecting continents, cross countries, interconnection of subnetworks, historically there were also many different technologies. Today, we also have Ethernet, and we'll have a closer look to PPP, point-to-point protocol, and optical transport networks, OTN. So you see here in boldface, Ethernet, PPP, OTN, these will be the topics here. Okay, so first PPP. What is this? Point-to-point protocol. Remember, we had those relatively simple NICs that simply connect one device with another device. Full duplex, that's quite common, and in between you have, for example, fiber optics. So we can have many different types of physical layers, but most common fiber optics connecting to different sites of a company, for example, cities. Here in PPP, we'll see we use the now well-known sliding window protocol for flow control, but we do not need medium access control. We all know why. MAC is not important. We only have one sender, clearly one receiver, and the other way around, one sender, one receiver. So there is no third node. So there's no need for medium access control on point-to-point links. So, but what we do need is we need special establishment of the connections processes for tearing down connections. We may need authentication methods, etc. So where do we find PPP? And that's a classical example. So since many years, we see PPP as a protocol to establish the connections for classical modems, but also for DSL systems where you connect your home network, for example, over a classical telephone line. That's the wire in the end, and with the DSL access multiplexer, or in former times with many other modems. And then we can run TCP/IP, our higher layer protocols, using PPP. So we have layer 4, layer 3 running over this layer 2 protocol, PPP. So what does PPP offer to us? So first of all, PPP has to establish a connection. So that's the first step. So we establish a physical layer connection. So we have to check if there's connectivity at all. So if the fiber is broken or not, if there's a link available. Then there's a second step to configure the network interface cards on each end of the link. What does it mean? Well, we have to agree upon maximum transfer unit, the size of a maximum frame. Depending on the technology, we may have different maximum sizes. Why? The point is, for example, in wireless technologies, you have way more bit errors, transmission errors. That means the chances to transport a frame without a bit error is higher if the frame is shorter. We have to agree upon escape characters. We have to agree upon so-called magic numbers to identify the ends, to detect loops. There's also mechanisms for authentication, and also we have to manage the termination of a link layer connection. And finally, we have a step 3, and that takes care of the network layer. So the network control protocol in PPP negotiates network layer options. So what is important here? Well, we need network addresses, the IP addresses, and maybe we have some options for compressing parts of the header, for example. We'll have a closer look into this when we come to layer 3, and there are also some procedures to tear down the network layer so that we free up the IP addresses. So PPP provides routines, mechanisms for the physical layer, the link layer, and the network layer to configure everything, to set up the connection. Furthermore, PPP defines the format of a packet, and here we exactly find what we learned in theory about flags, for example. PPP is character-oriented and uses byte stuffing, but reuses the format we know from bit stuffing, so we have a certain byte that is a flag, 0, 6 times a 1, 0. We have an address field. Well, it's useless. It's inherited from some other protocols defined during the time in the 80s. But here, if we have a point-to-point connection, that's useless. So it just has this format. So we carry some legacy with us. And we also have a control field that tells us we are in the so-called unnumbered mode. Unnumbered, that means no sequence numbers and no acknowledgements. So what we see here is basically that PPP took over some protocol elements from other protocol, HDLC, which is, let's say, more powerful, which has sequence numbers and can use acknowledgements, can have different addresses, etc. But in this case, we don't need it. We'll come back to this, what this means in the end, that we only use certain specific options. Then we have a special protocol field here, and this protocol field specifies network layer protocol. So, for example, if we have a certain value here, then this means we have IP as the next protocol. Then we have a checksum with a certain generator polynomial, and this gives us just the feature for detection, no correction. And then we have a AND flag. That's the idea. So you see, there was a other protocol, HDLC, and that had many options. But in this special case, point-to-point, and we don't want to have guaranteed deliveries or acknowledgements, sequence numbers, so we don't use all this. So it's kind of simplified. Yes, from today's perspective, we could have made it simpler, but those were the times. So how does it work to set up a connection? So it's a simple finite state machine. So we start in the status the connection is dead. Then we detect a carrier. So that means there's, for example, light on the fiber, there's some signal on the wire. So we start establishing this physical layer. Then we negotiate options on both sides. So that's for the layer 2. There's an authentication phase, and every time something goes wrong, we fail, and that means either connection is dead again, we terminate layer 2, etc. If authentication is successful, we set up our network layer, layer 3, and then we open the connection. So you see here those 3 phases. First is this one physical layer check, and then we establish the link layer, do the authentication, and then we establish layer 3, and then we have an open connection. Then, if everything is over, we terminate the connection, we drop the carrier, and that's it. So it's a very simple protocol for setting up the connection. And in a typical case, you set up the connection between 2 routers, for example, intercontinental link, whatever, and the connection stays there for a long time. Because then you start transmitting data over this connection. There also are many different frame types just to show you how this is done. So there is an initiator for this negotiation process of layer 2, and there's a responder. So one side is the initiator and says, for example, well, let's configure layer 2, and you have a list of certain values, and then the other side can say, okay, for this request, I send back the acknowledgement accepting the options, or I do not accept the options, or I even reject something, so I don't want to negotiate about this, etc. So these are just examples. So if you want to have a closer look into PPP, there are many standards. You see, they're a bit older. So this is really a protocol running now for many, many years, PPP. And it's basically it was the default for all dial-up internet access. So in former times where you had the modems, but PPP, you will find it still as one of the basic link layer protocols on point-to-point optical links or DSL connections, cable modems, and there you have some versions of it, PPP over Ethernet. So the idea is there to encapsulate PPP frames inside Ethernet or ATM. We didn't look into this. That you see, PPP is a very basic protocol where you say, okay, I want to structure the connection between two endpoints, and that's it. So no collisions, no medium access control, but somehow you have to set up the connection. Somehow you have to be able to configure both sides, and PPP does exactly this, configuring both sides. What is the alternative? You may ask, oh, why do we need a special protocol for this? So we just plug in our device and that's it. Yes, you can do this if both sides know all the parameters. So if there's only one parameter set, then it's easy. You just connect and everyone knows, yes, sure, we need this packet size. If we use exactly only the IP protocol, etc., then you don't have to negotiate. But in real systems, you always have to negotiate because we have different sizes for packets depending on if there's something wireless in between or not, and so on. So PPP is one way of doing so. Okay, so PPP was simple. Now let's have a closer look into the most dominant technology when it comes to local area, but nowadays also wide area networks, and why this is the case. Quick look into history. We already talked a bit about ALOA as a access mechanism for MAC layers. And so that was exactly the time in the 70s where we had this random multiple access for wireless systems. And also in the 70s, Xerox, a large company, did some experiments to connect their components in the printer business. So, and the idea there was, how can we connect components when we have sporadic bursty traffic? So from today's perspective, low data rate, but 3 megabit per second was quite a lot at that time, but sporadic. So we do not have this permanent traffic stream. And Robert Metcalf there thought of adapting this ALOA idea, but to improve it. And we already looked into this. Listen before talking, that's our carrier sensing, and listen while talking, that's the collision detection part. And that was the idea. And the whole idea there was called Ethernet, ether because, so that reminds at the times when people thought you need a special ether, something, some matter to transport electromagnetic waves. Today we know it's a bit different. The topology, very simple bus topology with some repeaters, as we'll see. And then over time, it took a while. IEEE came up with a standardization. Robert Metcalf founded a quite famous company, 3Com, and selling many millions of Ethernet adapters. So what was the basic idea? Just to see how this all started. And this is exactly what we have today in the situation in wireless systems. So we have the Ethernet, which was a thick yellow cable, coax cable, and you had taps, and you connected the devices to this ether, to the cable. In the end, we had a bus topology, very simple bus topology. That was relatively cheap because we needed only one wire through an office, for example, through an office building, and we could connect all the computers there, or one wire inside a larger system connecting all the components. But there, we already learned, okay, if one device starts sending and also another device starts sending, we may have problems, we have collisions in here, and we need certain mechanisms. So there are some problems. We know bus topology is cheap, but if there is a problem, where is the problem? If you have a damaged cable, cut cable, so where is exactly this the issue? So this is why pretty soon in many office cabling, star topology came up. So the idea here is that we have a central point and we have links from our computers to a central point. And if now something happens, well, this hurts only one link, but all the other links, they are still fine. So that at least the other computers can communicate with each other and we isolate only one computer. With a bus topology, with many computers connected to a bus, if you cut it here, then you create either two islands, or due to some problems in the propagation of the signal, if you have no termination here, you will kill the signals on both sides, so it will not work anymore. So, star topology is better, but it's more expensive. Yeah, you can imagine you need more wires. So in the very beginning, that was a very simple system in the middle, so-called hub. We'll have a close look into this. It's just repeating the signals. So if a signal comes in, you broadcast it on all the other wires. Very simple, and we still needed CSMA CD as a medium access control system. So nowadays, you typically use a switch, and we'll learn what a switch does. And so in a switch that we typically do not need any CSMA CD anymore. So in today's setting, if we have a switch as a central component, we don't need these medium access control algorithms anymore. Why? Because in the end, we have many point-to-point systems. So the computer connecting to the central element has a cable, and you handle between this central element and all the other computers connected to the central element this in a way that you have many point-to-point connections. Many of them. And if you have many point-to-point connections, there are no collisions anymore. So this is why today we don't need this, and also today we replace copper with fibers depending on the distance. So there's copper, as we learned in the last chapter, for certain distances, for higher data rates, up to 30 meters, yes, copper. But then depending on the topology, the distance and data rates we want to achieve, we may go to fiber. So in the end, the classical setting today, at home, in the office, or also in data centers, connecting computers, you have a switch, quite powerful switches, a star topology, and then at home something between 100 megabit and gigabit, and in data center something between 10 gigabit up to 100 gigabit per second or even higher. So that was the starting point of all this Ethernet, and although we typically do not use this classical CSMA CD any longer, we'll have a closer look into this because it's also the basic foundation for many wireless schemes. Although we don't use it, we still use the basic format of a frame, an Ethernet frame. And this is a quite famous frame, and you will find it all over in so many places, the Ethernet frame. So what do we have first? So first of all, we have a preamble. Why? In the typical Ethernet, there's nothing going on the wire. Nothing. Because you don't have to send anything. So there's not permanently some signal or whatever synchronizing both sides. No, there's nothing. So the first thing we need is some synchronization. And this is a 7-byte flag for synchronization. And so we have a sequence of 1010 and so on. And this synchronizes the receiver. We use Manchester coding on the classical Ethernet, and then the receiver is synchronized. And then we have a start of frame delimiter. And the difference here is, as you see, okay, there's a bit the end changing here. And this marks the beginning. Okay, then we know everything starts. The next, what we see is the MAC address. That's the destination address. So the MAC address of the receiver. This is a worldwide unique address given by the manufacturer of the device. So MAC address. Then we have a source address telling where does this packet come from. Source address, we will learn where we need this when we have a closer look into switches. Right now, just we have a destination and a source address like on any letter. And then we have a field that the semantics differs depending on the value in the field. So we have a classical standard that's quite often also cited. It's called Ethernet is 802.3. 11 is wireless LAN, for example. 15 is the basic Bluetooth, etc. But this is only true if the value of the field is less or equal 1500. Then this field is a length field. It indicates the length of the data that's coming after this field. And this is what the original standard says. Okay, industry manufactured many of these devices following the standard, but then had the idea, why not using this length field for the identification of the next protocol? And then it's interpreted as type field, telling, for example, okay, the next protocol is IP. What does it mean? And how and why is this done? Well, first of all, the how is quite simple. We use values larger or equal to 1536. This indicates that this field is now a type field. And the standard then is also called Ethernet 2, driven by industry. But what happens to the length? Well, the idea there is quite simple. Why should we use a length field? We have, at the end, a frame check sequence. And if we permanently, after detecting that data started, then we perform error checking and we simply define the end of the packet is as when the remainder, and this checksum algorithm, you remember, is 0. So as soon as the checksumming, this calculation, produces the result, no error, we assume that's the end of the packet. And this is why we don't need a length field. So we simply scan through data, and if everything is fine, then, well, the remainder should be 0. That's the end of data. And by the way, the packet ends. So we will recognize the end anyway. Using it in the classical 802.3 sense, we have a length field, and then we may have some additional logic link control in between on top of the MAC layer, etc., etc. But you see, so we have a basic standard, and soon this was enhanced then Ethernet 2, and this is one of the classical ways doing it. So if you check for this field, check the value, and then you will learn, is it a length or is it type? So that's the idea here. Then we have data, so that's up to 12,000 bits, so 1500 byte. We may have padding, so padding is required if there is no or only little data. Why? We will learn. So for the classical Ethernet, there is a minimum size required. Otherwise, medium access will not work. And then finally, we have our frame check sequence. So it's a 30-bit CRC. You've seen this already. So, and this CRC goes across destination address, source address, length type field, data, padding fields. So not over the delimiters. So checksumming starts here, because before that we do not even know what's going on here. So the checksum covers from the addresses across all the other fields and especially the payload. So a bit more about the addresses. MAC addresses, quite famous, 6 bytes long. Just a hint into the next chapter. This is more than the IP version 4 addresses. They're only 4 bytes long. So a MAC address is longer than the IP addresses. Just by the way. I will come back to this, what it means. So MAC address, how are they organized? So you have two halves. One is the organization, and the other one is the specific network interface controller address. Okay, first of all, what do we have inside this organization part, the first half? We have bits indicating if this is a unicast address, so packet frame intended for one receiver, multicast address, broadcast address. Broadcast, that means, okay, we send to everyone. So globally unique, that's the typical case, that we have addresses that are globally unique. By the way, you can change MAC addresses. So in former times, this was not possible, but today you can reprogram MAC addresses. So you have globally unique assigned by IEEE, or you have locally administered. So typically you have globally unique. The idea is that you, as a manufacturer of network interface cards, you go to IEEE, you buy a globally unique identifier, so for the first half, and then you can manufacture your NICs and assign your own addresses. And this gives overall globally unique addresses. The typical representation is hexadecimal, so this is the typical way with this columns in between, that I say, okay, this interface, this adapter has the following MAC address. And the MAC addresses are important because they will be used by switches to do certain operations. MAC addresses are not of interest for point-to-point connection, for example. I mean, why addresses? So we saw that the PPP, this protocol, well, didn't need any address, because point-to-point, yeah, you know the receiver. So you can check the addresses on your own, Linux, Windows, Mac OS, so you can find out which MAC addresses you have. And you will see typically you have several of them, indicated you have several network interface cards built in. Okay, that's the MAC address. And this MAC address is also used not only for the classical fixed Ethernet, but also in wireless systems. If you want to have a closer look, we already touched this issue. Please do have a look into Wireshark and check for yourself. They can go down and then check here, okay, what type of frame do we have? And then we see, oh, it's Ethernet 2. And then it also tells you, okay, for example, the source address is, here it says something about Intel, and then 3 bytes. And this exactly is our organization half of the address. And the second half, that's, well, the address then of this NIC. And altogether, it's the MAC address. And Wireshark already knows that this first half then belongs to Intel, for example. Or the destination in this case, so it's AVM, manufacturer of DSL modems. So here you can see the MAC addresses. And you also see exactly this if we have a individual address, so it's a classical unicast packet, and with a globally unique address. So this is the most common setting. We also see here that the type now, what follows, is an IP packet inside this Ethernet frame. So Wireshark tells you it's Ethernet type 2, tells you the MAC addresses, and tells you also inside the MAC address who actually created this address, etc., and tells you, this is now an IP type IP packet inside. And then, but this is then layer 3. It also tells you what is the source address of IP, destination address, and so on. And if we click on this little plus sign, we then see what's inside the IP packet. But this is then layer 3. Here we are on layer 2. Okay, and even Wireshark also gives you a bit information about the physical layer, if possible. So that is the setting, and we'll briefly go through the classical medium access. Why do we go now through the classical medium access? It's not because today we still use it, and it's also not to bother you with old historical stuff. The point is, this shows you how you can organize medium access, and if you have the situation where we have a bus, then why not using this? And this is then important for the course mobile communications, where we see, can we use it and how do we organize it in wireless systems? Because in wireless systems, we cannot have individual cables between a device and the antenna. There are some special tricks, but more about this in mobile communications. So the very basic mechanisms, remember Robert Metcalf, we had this bus topology. And the MAC scheme is based on CSMA CD. So listen before sending and stop as soon as someone else sends. So that's the idea there. Remember, that's the setting of a classical TV discussion where people just sit there and then talk to each other, and as soon as you want to send something, you start sending. And then if someone else also starts at almost the same time, you may stop and then send again, etc. So the first step is always checking if the medium is available, and then you start with your transmission. Now you have to remember something. We are working here on a copper wire, and then roughly the speed of our signal is 2/3 C. So it's not really speed of light, but that doesn't matter in the end. So it's not infinite. So what could happen? It could be the case that although you already started with your sending process, another station thinks, why not also sending something? So this could be the case. So it could be the case that the other station also starts sending, and this creates a collision somewhere here, and then the collision propagates along this wire in both directions. Okay? And because you do this listen while talk, the collision detection, you will be able to detect the collision. So basically you compare your signal with the signal you see on the cable, and if there's a difference, oops, there must be a collision. So, and the same is true for the other station. In the classical CSMA CD, we had then the stations sending a jamming signal and stop transmission. So you detect the collision, and if you say, there's a collision, you do not only stop, but you send a strong jamming signal. Why? This tells everybody there was something going wrong, so stop all activities and continue with the binary exponential backoff. We had a look into this. So this is very simple. We do not have any centralized coordination here. There are drawbacks, as we learned, no guarantee access, and it could be the case, depending on the traffic on this wire, there's a large delay, so you have to wait a long time before you're allowed to send. Okay, so it's simple, this is why it's used, but you cannot guarantee anything. So, what happens after a collision? The problem is that if you send a jamming signal and several stations noticed, there was a collision, I wanted to send something, or I was already sending something, that's the point, then, okay, how long do we wait? And the point is, we have to use a random waiting period. Why random? If you do not use a random period, then all the stations try to send at the same time again, and we have a collision again. So random, that's the first thing. Random, we have a certain interval, okay? We have a certain interval, and waiting there, okay, maybe I'm in a hurry, so I don't wait, but it's random to some value, whatever, x. So we pick a random value here. That's the idea. So in the beginning, you try to keep the interval small, because if you have a large interval, it could be the case you keep a high random number, and that means waiting for a long time. So problem. But if the interval is small, a fixed small interval, you have a high risk of subsequent collisions again. So what is done? You have a random waiting period, but you have an increasing interval. So your interval is not fixed, but you start with a small interval, and what you then do is you basically increase the size of the interval. The idea here is you double the size. So after the ith collision, you draw a random number x from a certain interval 0 to 2 to the power of I minus 1. And after a certain number of collisions, here by definition after 10th collision, you fix the interval, it does not double, and after the 16th collision, you simply give up. Because then something is really going on the network and you cannot heal it and whatever. So maybe there's some interference, etc. So that is the idea. So you have a certain waiting interval, so random interval, and you pick a random number. If you experience a collision, that means you detect jamming, then you double the interval. We'll come back exactly to these mechanisms in the classical wireless LANs. So after collision, the channel is free again, and then you wait for this X time slot, and then you try to transmit again according to CSMA CD. That means you perform carrier sensing. If the carrier is busy, then you have to wait. If not, then you can send, and a collision can happen. So in the classical Ethernet, you had a certain slot length, and you also have so-called conflict periods. Why? We'll come back to this. So the standard defines exactly this, the intervals, the waiting, that is after 10th collision you fix it, and maximum 16 collisions. This is all in the standard. So what does it mean? What is the advantage of doing so? We can adapt. We can adapt to different traffic loads. Well, if there's only light load, we have no collisions, well, fine. If the medium is idle, we just send, so very low delay. If there's light low and we had some collisions, we still have small intervals. That means smaller random numbers, statistically. And that means shorter waiting times. And if the load increases, we pick randomly out of larger intervals, and that spreads out the random values and lowers the chances for collisions. That's the idea. So small waiting, short waiting, small intervals with low load, large intervals, better distribution of these random numbers if we have more traffic. The problem is this can be unfair. Why can this be unfair? Well, what happens if you just approach or try to access the channel the first time? Those new nodes, they don't know anything about the history of collisions. So we have one problem with new contending nodes. That's one of the problems, because assume you just hang on this bus and you did not participate in anything. That means you do not count collisions. So you do not increase your interval. If you're a new node, you still have your small interval. And all the other nodes that experience a lot of collisions, they already have a large interval. So statistically, they will lose against this new node, because the new node statistically picks a lower random number x. Compared to the other, statistically, they may pick larger random number x. So it's unfair. Plus, if someone wins the contention, then this winner says, hey, no more collision, because, well, I picked a certain random number, maybe lower than the others, so I was the winner. I waited a shorter period of time, no more collisions, and then also the contention, this window where you pick your random number from, shrinks again. And that means, well, it's a bit unfair. So, remember, simple scheme. It's not coordinated by some central device. All the devices have to look at the medium, and they all store their history, basically, in terms of how large is my interval. It's a bit unfair, but it's simple. So, but why do we have, now coming back to this minimum packet size, we had this padding field to create at least a minimum size? Well, this has to do something with the detection of collisions. The problem, as I already indicated, is we have a finite propagation speed. That was our 2/3 roughly of the speed of light. So it could happen that two devices send at the same time or almost the same time, and you do not detect that the channel, your cable, is already busy. So a node thinks, well, it cannot think, but thinks the channel is free. One other node just started transmitting, could be exactly the same time or a bit earlier, because it takes a while before the signal travels to your node. So while you send, when should you stop listening? Should you listen all the time? Well, maybe that's not necessary, because as soon as someone started sending, then, after some time, all the nodes should hear my signal, and then according to this mechanism, no node should then access the medium, because we do carrier sensing. So the question is, what is the maximum conflict period? This depends on the maximum range in the network. So imagine, now we have time here on our y-axis, on x-axis we have the distance, maximum range between two potential senders. Remember, we had this in the beginning, long yellow cable, we had the terminators, and then we had this long cable. So we picked the two stations with the maximum distance connected here to our cable. Maximum range, the maximum length of the cable. So first of all, one station starts sending. So that's S1 starts sending. Then our signal travels along the wire. Then after just a while, station 2 starts sending. And why can station 2 start sending here, roughly here? Because you see, at this time, the signal did not reach the station. So the signal is still somewhere here on the way. So you create the signal, it continues, and then it's somewhere here, and then you start sending. What happens then? The signal continues to travel, but also this signal starts traveling, and we have the collision here. So we have the collision, and then when do we detect this collision? Well, in this case, exactly when the collision is here at station 2, because then the collision continues propagating with 2/3 speed of light, and then this is exactly when we have the collision. So the point is to be able to detect this collision and to be able to send back a jamming signal. Station 1 still has to be active. Imagine station 1 sends some data and then stops sending. We learned we perform collision detection. So we listen into the medium while we send for a certain time. Imagine now we stop sending here for S1. So S1 stops here. That means when the collision here arrives at S1, we do not listen to the medium anymore. So we never noticed that there was a collision. Just imagine we just send a short signal and then go to sleep again. We will never recognize that there was a collision. And this is the reason why we need a minimum sending time depending on the maximum range of the network. Because in the worst case, the collision happens right before sender S2. So it takes a while to travel all along the wire with the maximum range. Then the collision happens right before S2, and then it takes exactly the same time to travel all the long way back to sender S1. And this is the minimum time we have to be active as sender 1. So we need a minimum sending time, and this then gives us a minimum packet length. So the sender should be active at least as long as it takes for the signal to travel to the most distant other receiver and back. And this gives us then, when we do the math, a certain minimum payload at certain data rate with a certain round trip time, here 50 microseconds at a certain distance, etc. Some safety, some guard time in between. So in the end, this is how we come to these 46 bytes for this very initial standard of this 2.5 kilometer Ethernet. Because it could be the case that we have a basic distance of 2.5 kilometers from one sender to another and 2.5 kilometers back, and then we notice that something went wrong. And this is the time how long we should be active. And this limited the distance here. And this, by the way, is one of the reasons why these mechanisms have to be adapted to the wireless domain, because there we cannot limit the distance. We don't have a maximum wireless distance, something like this. Like here in the cables, it's written in the technical specification, maximum 2.5 kilometers. Okay, so that was the beginning of this very classical CSMA CD. And then, the engineers tried to, how can we adapt several stations? What is the maximum length of a cable? There we have problems of attenuation of the signal. Repeaters have been introduced. So the idea of a repeater is we take in the signal, which is relatively weak, a weak signal, but the repeater knows what it means, creates ones and zeros out of this, and can then create a nice, perfect, strong signal again, the output. So a repeater is not just an amplifier. So amplifier can amplify analog signals, so you also have a weak signal, but it makes simply the signal strong. It amplifies also noise. Here with repeaters, I regenerate the original, hopefully the original data, and can then create a perfect new signal. And this is why, in theory, we can repeat digital signals for an infinite distance. So there's no reason why there should be a limit. Analog signals, this is not possible, because you will have more and more noise. You don't know what the signals mean, and you amplify also noise, so there's an upper end. Here we have an upper end to the limitations of the protocol. But that's a different story. So maximum range for Ethernet, we learned this 2.5 kilometers roughly. And you see here, this is then the maximum extension. Those were the classical installations. Okay, so a bit history, but still the implementation we have today still has some of the history in it. Also the classical Ethernet, we know this already, used baseband encoding, Manchester, here plus minus 0.85 volts. So we know this Manchester coding with the edge in the middle of the bit. We know we have no direct current, we have nice clock synchronization with each bit, but we also know that we waste half of the bandwidth due to this fact that we may have the several transmissions, 2 transmissions potentially between per bit. So this is how all this started, and then over the years we had many more standards developed based on this 802.3, but the higher data rates, they do not use the CSMA CD any longer. So no 10 gigabit network uses this anymore. So this was, I would say, a bit also for marketing compatibility reasons. We kept the name Ethernet and we kept the CSMA CD, although from, I think, using 100 megabit Ethernet onwards, we had only star topologies and switches. So it started with this original standard, 83, with then cheaper versions with thin coax cables. Then we had standards for twisted pair, starting with hubs and the first switches coming up, 1990, 95, then also different fiber versions, and already 100 megabit per second since 1995 are quite famous, this type of cabling, 100 base TX. And then 99 already gigabit Ethernet, 1000 base T, so over copper wires. And then 10 gigabit, 2006, but also over copper wires. But with fiber, we can go up to 10 kilometers, 30 kilometers. And the success story continues with 40 gigabit per second. Well, only 30 meters, but this is typical for data centers, but with fiber optics up to 30 kilometers. So you see, this is already fine for a metropolitan area network. 100 gigabit, now it's already there available. You see also with monomode fibers, also 30 kilometers. Copper only for short interconnect in compute centers. And then a bit newer standards going up to 200 and 400 gigabit per second with 10 kilometers using DWDM, so wavelength division multiplexing with single mode fibers. But that's not the end. So currently there are task forces working on 400 and 800 gigabit per second, and the standard should come out next year, 2024. And there's a task force working on up to 1.6 terabit per second with standard expected 2026. So you see, a single technology, well, yes, it's a certain packet format, but no more CSMA CD for the higher data rates, and depending on the physical layer, really different distances covered here by Ethernet. So this table comprises different standards, well known, the classical Ethernet, fast Ethernet, gigabit, and 10 gigabit Ethernet. So you see the typical settings for 10,000 megabit per second. And what's quite interesting to see is minimum frame length. We learned we need a certain minimum length due to the problems with CSMA CD. And you see for gigabit Ethernet, this is longer. Why? Well, you can imagine you send more bits per second, but we have to maintain a certain minimum duration of listening to the medium. And this is why the packet has to be longer. Also for 10 gigabit and higher, so we typically have longer packets, we have maximum frame length and different signal representations. Manchester coding, that was our classical line code, but for higher data rates we have 8B10B and even a bit more complex schemes. So you see the basic ideas of Ethernet state, but then we have certain slight variation. Just a quick tour through a bit of the history so that you can come back and see, okay, this is how it developed. So we had this very simple so-called Cheapernet, 10 megabits per second, where we had a coax cable and BNC connectors. So with a certain maximum expansion, so it's not the 2.5 kilometers, so it was a simpler version, but very successful. So that was the classical cabling in office, university, buildings, etc., where you simply connected the machine with Ethernet coax cables and connecting them with one single coax cable going through all the machines. So that was the first well, local area network technology that was affordable for the masses. Then pretty soon everyone noticed that having this single wire has the problem of the detection of some errors. If you cut the wire, or if someone disconnected this at the BNC plugs, disconnected the cable so that you didn't have this one cable going through all the stations, well, the whole network was down. So that was a problem. So pretty soon the first hubs came up, connecting the machines in star topology. So with a typical cable length of up to 100 meters. And the hub was a very simple thing, simply broadcasting everything that comes into all the other directions. And this is also where we started to use the RJ45 plugs. So quite old standard, but still today you see versions of these plugs, the RJ45 registered jacks, going back to the early 70s. But also the first fibers came up. The fiber with different types of plugs, ST, SC, etc. And you saw them pairwise. So for the directions, in here you had the fiber cores, some cladding around this, etc. So fiber was expensive, but was very nice when it comes to noise. So it was to connect the buildings. So that was the starting point with 10 megabits per second. Still using the Ethernet basics, CSMA CD, but faster was then the so-called fast Ethernet. Fast Ethernet was similar to 10 base T, was now 100 base T, etc. So 95. But the problem now is, okay, what about the frame length? Because we know for the classical Ethernet we had this 64 byte, but now we are 10 times faster. And one way of handling this was, okay, we reduce the maximum distance by a factor of 10. We learned the problem is we have two senders. We had this maximum distance. This is where it all comes from. And we learned this was up to 2,500 meters. So if we stay with the same minimum frame length, then we simply cut the maximum distance. So for example, to around 200 meters. So that was the idea. Auto configuration was introduced, so negotiation of the speed, so either 10 or 100. This can be done automatically. Also, if we have half duplex, full duplex, how we use our wires. So fast Ethernet comes with different types of cabling. So one quite common one was twisted pair, category 3, relatively cheap, using all the cable pairs. There was also a version with, well, a bit more expensive cabling, category 5 cabling, which is better. So using only 2 of the cable pairs, 1 for each direction. So then we can have full duplex. And we also had a fiber version. So the 100 base TX, that is really the most used 100 megabit versions, and you can still find several installations of this. Okay, but this was not really fast enough, so the next step was the Gigabit Ethernet, as you already saw in the overview. Gigabit Ethernet start also with fibers, but there's also a copper version. It should be compatible to fast Ethernet and Ethernet. And now, what was the alternative? So going from Ethernet to fast Ethernet, we reduced the max distance from 2,500 meters down to about 200 meters. So one solution would be, okay, maximum now 20 meters. This would be very, very, very local area network. So there was the alternative, that was the solution. We increase the minimum frame length from 64 to 512 byte. So that was the idea. But what happens if we do not have this data? Then we append an extension to our frame. And that's called the carrier extension. And this is the idea that we add after the frame a so-called no data field. The no data field is added by hardware. The software does not notice anything from this. And if you pass then the frame from Gigabit Ethernet to Fast Ethernet, you simply remove the node data part. Yes, this wastes some of the data rates we could have on Gigabit Ethernet, but doing it this way, we are still compatible. So Gigabit Ethernet is also the last version that really uses this CSMA CD scheme. So auto configuration, again, half duplex, duplex, and there's also something introduced that's called frame bursting. So if you notice that you have several frames, why not concatenate them? So this sending no data is not that nice. So why not concatenating several MAC frames, and then there must be something in between, so you just have frame, 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 and in between there are so-called interframe bits, and that's here, that's a gap, this interframe gap, and then you have something that's going on the medium, so that all the other controllers will notice, there's something going on, we are not allowed to access the medium. Typically, if you have Gigabit Ethernet, then we use also switches, no hubs, and in the end, as we do not have collisions anymore, the maximum cable length is now only determined by signal attenuation. So if we have a switch in between and you have your computer is connected to the switch, you have many of the point-to-point connections. So there is no more collision if we additionally have a full duplex connection. And this is the typical setting there. So we can also do this for backbone in metropolitan area network. Why not? So you see how a technology that started in a very local area network now extends to metropolitan area networks, and depending on the physical layer you use, well, this is limited to only, you see, for example, 100 meter, a typical setting in office buildings also today, using different categories of cabling, so very cheap cabling, or there are other versions with multi-mode, monomode fibers, then you can bridge 5 kilometers, for example. As you know, the story didn't end here, so we have 10 gigabit Ethernet, and this is typically using a switch and optical fibers, and this was also the end of CSMA CD. So to be precise, this is not really Ethernet, a classical Ethernet any longer, but for marketing, etc., well, it's still called Ethernet. Plus, for compatibility with the older versions, it's still the same frame format, same frame sizes. So it's way easier to interconnect 10 gigabit standard systems with 1 gigabit, 100 megabit, etc. systems. Using monomode, we can now go into metropolitan and wide area networks. And there are different physical layer specifications. So physical layers using 10 gigabit or specifications compatible with technologies. We'll not have a closer look. This was a classical technology coming from the telco domain, so telecommunication. This is where we had thousands of voice streams multiplexed. So you remember we had those many 64 kbit per second or US 56 kbit per second voice streams, multiplexing them with a very strict time division multiplexing, round robin. We multiplex and we have several hierarchies of multiplexing, and this is where we end up with this 9.6215 gigabit per second. There are copper versions also for the 10 gigabit Ethernet. They also exist. So it's a bit more complicated. You can imagine interference, copper wire, etc., but it works. So, but typically we use fiber optics, and you see many different standards here with different physical layers, different ranges. So for a typical building or compute center, or we go for wider area networks up to 40 kilometers with these single mode fibers. And you see the coding is a bit more complex, using different wavelengths, etc. So what you also see here is that we have serial transmission. Serial, that means we use one wavelength. So for example, 1310 nanometer serial transmission, we use only this wavelength. Or we can do wavelength division multiplexing. So in this case, we use 1, 2, 3, 4 different wavelengths at the same time, and we then split the traffic stream into those 4 different wavelengths and transmit it this way. And also there are these typical endings when you see those conventions for the naming of 10G base Ethernets. You see it from here, it's extended, for example, or long range or short range. So these are typical acronyms here. So that's a standard version using fibers for short, medium and long distances. And yes, we do have copper versions. That was really impossible just some years ago to bring 10 gigabit per second over copper. There's a version for coax wire cabling. That's typically for compute centers, 15 meters, connecting different racks. But there's also for typical office cabling, if you use Cat7, Cat8 cables, then you can bridge 100 meters. So that's quite a lot. There are special filters integrated to separate sending, receiving signal. So it's a bit more complicated, but, and this is the important part and a part of the success story, we keep the old Ethernet formats. So this means you do not have to convert the formats from one type network to another one. We'll see at the end, there's also another fact helping us a lot. We do not really give hard guarantees to higher layers. I will come back to this. So what else do we have? High-end versions. This is shown here. We have the, as I showed in the overview, the 40, the 100, 200 and 400 gigabit per second standards available. But we also already have not only the standards, but also devices. For example, 800 gigabit per second per port, which could be used at, for example, 2 times 400 gigabit Ethernet, and the total throughput of such a device 28.8 terabit per second. This is quite a lot. So we have 36 ports. You see, these are the ports, and you could have then, for example, 400 gigabit Ethernet ports here. So, and as I already mentioned, this even goes to higher data rates. 1.6 terabit per second will come up soon. That's quite a lot. And we still have basically Ethernet technology. And as I said, one advantage is same frame format. So we do not have to convert, which is a problem at really high speeds. I mean, talk about 800 gigabit per second. So just do the math and check how long in seconds is a single bit. So that's not that long. Just something to mention, because you might stumble over this reading standards. There is something else also in layer 2. And why didn't we explain this, focus on this? I'll tell you why. So Ethernet and the 802.3 MAC offers best effort. Well, what does it mean? We offer unreliable datagram, no acknowledgements. I remember PPP also unnumbered frames, so no acknowledgements, nothing. So, what happens if you want to provide reliability? Then you need something in addition. So you need in addition a layer, and this is called the logical link control layer, that then, for example, offers a reliable connection-oriented service or acknowledged datagram. This is where we need, for example, sequence numbers. This is where we need a connection setup before we actually transmit data. And this additional layer has been standardized by IEEE, and that's the standard 802.2. And the idea there was, well, we can have different MACs, different physical layers. So there could be also a MAC, I briefly mentioned token ring, and could have a complete different PHY, and there could be yet another MAC, etc., with different PHYs, etc. So that was the idea, and the LLC layer introduced an own header with destination access point, source access point, several control fields for this sequence numbers acknowledgements. So why didn't I explain this? Well, we don't use it. So the whole working group's disbanded, and the Ethernet today offers unreliable datagram only. So in the end, yes, there was a lot of standardization going on, and you saw also legacy in PPP. We see legacy when it comes to the layers, and in the classical textbooks you will always find there's a MAC layer, there's LLC, and there are many other fields defined. But in real systems, we use Ethernet, offering unreliable datagram only, that's it. And the Ethernet offers this to the higher layer. And the typical higher layer here is IP, the Internet Protocol. So why bothering about reliability, acknowledgement, etc., if we have a layer 3 protocol that is unreliable, packet-oriented, unreliable. So typically we don't have this. We simply have MAC layer, and that is typically an Ethernet MAC offering unreliable datagram service, no acknowledgements. So some questions before we come to the infrastructure. So now I'm pretty sure you know the dominant networking protocol on layer 2 for local metropolitan wide area networks. But why is this the case? And I just said that Ethernet does not offer any quality of service, acknowledged, reliable transmission, connection setup, etc. So, how can we now offer delay-sensitive applications like voice over the system? Things we could not think of many years ago when we started all with this classical Ethernet 10 megabit per second. Why do we need a protocol like PPP? Why can't we directly send IP packets over the link? Why doing this PPP? If we look back, looking at Ethernet today, so what remained? And look at the original standard, what was dropped and why could we drop some part? Go ahead, use Wireshark, check the packet flow on your network adapter. This really gives you a lot of insight. You will learn a lot more about Ethernet and how it looks like, what the addresses are, what is the typical data flow. You will be surprised seeing what's going on, who's sending data to which device, etc. And this helps you a lot in understanding all the architectures.